Thanks so much, Anne-Marie. It's a pleasure to be with all of you today. I hope you enjoy the presentation. I'm going to share my screen and we'll get started. As Anne-Marie noted, we are going to talk about acoustically distinguishable spaces today. It's a mouthful. I get to say it like 300 times, so we'll try to make it as enjoyable as possible. We really want to understand this term, and for many, it's still a new concept, and so that's why we thought we'd do a deep dive into this topic. We're going to do that in separating it into 4 sections. We're going to first talk about the definition of an acoustically distinguishable space and really what's its purpose. Why do we even have it, and why do we have these responsibilities? And then we're going to talk about how a designer, particularly someone putting together, let's say, a shop drawing or design drawings, how they can define a space and how they can show that. And then, of course, how that leads to the implications for the authority having jurisdiction during acceptance testing and how these are related topics. And our last section will be how, once we have our design, how can we improve our design? How can we make a space more intelligible? What kinds of tips and tricks can we do to make these spaces better? First, I want to share that because I am on several NFPA technical committees, including NFPA 72, Chapter 24. I'm not speaking on behalf of the National Fire Protection Association. We encourage you to purchase a copy of NFPA 72 from NFPA. And if you're using it today, we're going to be using the 2016 edition as references. However, I will be giving some updates for the 2019 version in case any of you are using that in your local jurisdiction. All right, well, let's jump right in. Let's talk first about the definition and purpose of an acoustically distinguishable space. And of course, that's going to start with what is an ADS? Well, here's the definition that appears in the 2016 edition. This was an entirely new term to the fire alarm industry, and it was added in the 2010 edition of NFPA 72. And this definition has not changed in any of those, including the 2019 version, and we're currently writing the 2022 edition, and as far as I know, this definition is not changed. So really it breaks down to spaces that might be enclosed or otherwise defined that are distinguished from other spaces because of different acoustical, environmental, or use characteristics or other properties. So really what we want to do with this is break this definition into 2 pieces. We want to first look at acoustic properties of spaces and what we can learn about spaces from the construction, and then how they're distinguishable, how we can kind of group these spaces to be different one from the other. Now, acoustic properties, every space has acoustic properties. So what we're trying to do is group those spaces that have common acoustic properties. Well, of course, it's the physical construction that determines how the acoustic properties of a space. So we start with floors, right? So floors may have tile, they may have carpet, they may be usually they're very hard surfaces and reflective surfaces. You can kind of see that in the picture. This is just a concrete floor, a very hard reflective surface that affects how sound moves within the space. Next, you have your ceilings. Your ceilings have a lot to do with how sound moves in a space. We often, in office buildings and other spaces, have acoustical ceiling tile, which is very absorbent. Or we might have hard lid or even cloud ceilings that bounce or provide reflection of sound signals off of them, greatly increasing the difficulty to provide adequate sound within the space. And of course, the height has a big influence on it. And you can see again in the picture, we have kind of an atrium looking space. We've got a very hard ceiling in that it's a glass atrium, so very reflective, and it has a lot of volume to it. And then finally, we have to look at the walls. We have to understand what the walls may be made of. Maybe we're dealing with glass curtain wall like you see at the very end of the space in your picture, or drywall, as you commonly see in most buildings today. fabric. We can have fabric on the wall or other absorbing materials that can greatly improve the sound characteristics of a room, or even like you see in this picture, brick or steel or something else that might be highly reflective. So the physical construction makes up a lot of these common acoustic properties that we might see from space to space. Now, we also need to consider the environmental properties of the room. This is things like loud fans or equipment, like we'd see in a mechanical equipment room or an elevator equipment room. If you're in a hydraulic elevator equipment room, obviously it makes a lot of noise when that elevator is moving up and down. Mechanical rooms may have a loud air handler in them or a series of fans that create an ambient sound pressure level all to themselves. We may have workshops or plants or mills or assembly lines that have environmental noise from the machinery that's located within them, and we have to compensate that and take that into consideration when designing for sound. High occupancy load, like we see in a passenger hold room of an airport. I work a lot in airports, and actually humans are very sound absorbent. Humans inside a large space actually help the sound characteristics of a space. And also the existence of any sound sources that may be within the facility. And that's not just, let's say, a sound system that's playing music, although that could be. But you can take this example. This is a mall in Las Vegas attached to one of the casinos, and we've got this big waterfall right smack in the middle of the atrium. Well, this creates almost like a white noise, but it's this constant noise that you have to overcome, or at least be prepared to deal with when designing the sound for a given space. And maybe even more difficult or challenging spaces. This is a picture back when we all could travel of the JW Marriott in Orlando, Florida. Very, very beautiful facility, but you see the hard terrazzo tile, marble type flooring, marble columns, marble tiling on the walls. It's very high, a lot of volume, very difficult acoustics in this space. This space was actually provided with 4 regular fire alarm horn strobes. It would be very, very difficult to provide intelligible voice inside a challenging space like that. And then we also look at spaces that have common use. And this is where acoustically distinguishable spaces becomes fairly easy to identify because all of these similar types of rooms are kind of grouped together. The best example is like a restroom or a toilet. These spaces are all the same for the most part. They are usually fairly difficult to provide intelligible voice inside, but from a use standpoint, they are kind of the same every single time. Offices are very common. You usually have tile floor or carpeted floors, acoustic ceiling tiles, drywall on the walls. So really an office is kind of what we're saying. And other rooms, break rooms, conference rooms are kind of very similar. Corridors and stairwells are also going to have very common use and really can be handled the same. And that helps us speed our process when identifying these different types of acoustically distinguishable spaces. Now, the second half of our definition it deals with the distinguishable space part. So it gives in that definition a couple of things that we could break down a distinguishable space into. And the first thing it notes is a notification zone. Now, it's good for us to remember what a notification zone is. It's a term that is defined in NFPA 72. It's a discrete area of a building bounded by building outer walls, fire or smoke compartment boundaries, floor separations, or other fire safety subdivisions. And all of those spaces receive common notification. And really the best example of a notification zone is a floor, a single floor of a high-rise building. That whole floor goes off or alarms together. In most cases, that would be your notification zone. So it's possible, given the construction of the building, that an entire notification zone could be an acoustically distinguishable space. But as we saw with the earlier breakdown of how the rooms are used, we often have stairwells, restrooms, conference rooms, corridors, all of those things. We got to take that into consideration. So normally we have to break down the notification zone into some other subdivisions, to subzones, to really narrow down how we're going to lay out our system. And again, these could be enclosed spaces or otherwise how we define the space. In fact, they can have real or even imaginary boundaries. And we're going to touch on that towards the latter part of our presentation of how we could have an acoustically distinguishable space with an imaginary boundary. Now, before we look at a few examples of what we're talking about, we need to remember the purpose of an acoustically distinguishable space. The whole purpose is to define what spaces will have voice communication capability, and of those spaces, which will require full intelligibility and which will require something less than that, either no intelligibility or some lesser form of intelligible voice. Now, this is done with the express purpose of being able to provide the correct code requirements for the design of the space. And if we understand how to design the space, then we can understand how to commission or test the space during acceptance testing in particular. Well, let's take a look at an example, and we'll kind of use this throughout our presentation as an example building because it presents some interesting challenges and situations. Now, this is a visual and performing arts center located on a university campus. This building has been built and it's in use. Quite attractive of a building. It has 4 performing arts theaters, as well as rehearsal facilities, storage rooms, offices, dressing rooms, elevators, restrooms, showers, mechanical spaces, even pre-function spaces and lobby spaces. So pretty typical, but a wide variety of spaces and uses. And we're going to use this building as an example today. Now, what do we know about this building? Well, we know first and foremost the building code requires this building to have an emergency voice communication system, an EVAX system, a voice fire alarm system. There will be some house sound systems in place, which is kind of unique in a building. We don't always have that, but in this building, obviously the theaters are equipped with professional house sound systems. There is no building-wide paging system or public address system. So really the voice fire alarm system is all we've got to reach the vast majority of the spaces within our building. And the building is a single notification zone. So it is a general alarm building. Everything is going off on once. But really, like we talked about, in this case, we couldn't make this one building just because it's one notification zone, one acoustically distinguishable space. So really what we have to start doing is breaking the building into smaller pieces. Well, that begs the question, why not just require intelligible voice everywhere and have one acoustically distinguishable space? Well, that would be great for the designer. I mean, that would be ideal, but it's simply not practical or even desirable for a number of reasons. And we hope to be able to highlight some of those reasons for you today. Now, in order to understand why we can't have just one ADS, we need to understand really 3 things, or at least have a grip on 3 things. The very first thing is the system's mission or purpose. This will define where intelligible voice is really needed. Now, let's take a group of offices as an example. Now, in this case, each small office, or perhaps the whole group of small offices, could be defined and probably should be defined as an acoustically distinguishable space. Now, if the emergency communication system or fire alarm system that we're placing in this building is used for paging or music, then a designer might place speakers in each one of the individual offices to provide that intelligible voice in those spaces. And that would be in addition to the speakers placed out in the hallway, for instance, because obviously that's a common use area and we need to provide alerting in there. However, if this emergency communication system is really only being provided for emergencies, the designer might not designed for intelligibility in all the offices and might rely instead on speakers only in the hallway. Now, ultimately, the intelligibility would have to be determined by how much sound will penetrate the office doors, and we can do those kinds of calculations where we can understand how much sound may be going through the door and make some good logical decisions about where it might be intelligible and where it would not. The second key thing we need to remember is cost. Everything costs money. Obviously, providing speakers in every office in addition to the hallway is going to be more expensive, especially when considering insulation, wiring, amplifiers, all the things that go with that kind of a design. The third consideration is intelligibility really possible? Well, in our office example and our corridor example here, it is quite possible. We're dealing with a 10-foot drop acoustical ceiling tiles with carpeted and tile floor. It's quite possible to provide a nice intelligible design in these spaces. In fact, it's fairly easy to do so. However, what about this space? Now, this is the main lobby, which is really better referred to as the pre-function space for the main theater. It has a glass curved curtain wall with a terrazzo tile flooring and a 25-foot high hard lid ceiling. This is a highly reverberant space, and a high degree of intelligibility may be difficult, if not impossible, to achieve. Now we start to see why the whole building cannot just be one acoustically distinguishable space. We have to look at all of these different kinds of scenarios. Let's look at some other spaces in this building. Now, toilets, as we mentioned, are individual spaces, whether they're an individual restroom or a group restroom. These have long relied on visual notification only, and that's because of the physical construction of restrooms makes it quite difficult to achieve intelligibility. Horns and pretones can be disruptive and speakers ineffectual due to the hard surfaces within them. Dressing rooms and lactation rooms present different challenges. Folks may not even be able to leave the space to understand the message. So maybe we need a higher level of intelligibility in these spaces that people can't necessarily leave or exit the room to hear a message intelligibly. And if we're providing speakers in these kinds of spaces, what's the ambient noise level? And thus, what is the alarm level? What should it be? And obviously, that might be much different from a dressing room to a lactation room. Obviously, it's going to be very, very quiet for a nursing mother in one of those rooms. So if we're providing a speaker, we probably want to be very careful about how we provide power or the wattage setting that we set for that particular speaker. Elevator cabs. Now, obviously, that's different from a small building like the one we're dealing with here to a high rise. In a high rise, we would put a speaker in an elevator cab. But again, we have to think about the close proximity that people are to the speaker, and we'd want to be very, very careful about how the wattage that we applied to that speaker. A couple of other spaces to think about. For mechanical spaces, we have to think about what kind of equipment is installed. Now, this is an electrical room or a comm room. Those might, even though they're mechanical type rooms, they might actually be quite quiet. But we, again, would have to kind of know what kind of equipment is in there. But perhaps an electrical switchgear room might have a crack unit in it or some other kind of air conditioning unit to keep the equipment cool. So we'd have to think about the mechanical equipment that might go into it. Boiler rooms, mechanical rooms vary from purpose to purpose. They may be different. A boiler room might be quite quiet versus a mechanical room that has a large air handler or series of air handlers in it that has its own ambient sound pressure level. So we have to do a little research, and we also have to start thinking about maximum sound. What if that boiler room or the mechanical room has an ambient noise level of 90 dB, for instance. Well, that would mean our speakers need to produce 105 dB. Well, we're getting very, very close to the upper end of where we have to be or where we should be. So we got to be careful when we take a look at some of these spaces. Now, stairs, again, are much like elevator cabs. They differ from small buildings versus high-rise. We wouldn't put speakers normally in a stairwell in a small building, but in a high-rise, we frequently do every third floor or something like that, put a speaker so that we can have manual voice capability into the egress stairs. So that's something to consider. And stairs create quite a challenge, right? Because really they're a series of concrete boxes and often and make it quite difficult to achieve intelligibility. Storage rooms may be more than just storage. You can see in this case, it's given a storage room label, but in reality, it's an usher's room. It's a locker room where people can stay and sit and be for quite some time. So rather than just dismissing this as a storage room and not requiring some form of intelligibility, maybe we need to pause and think, how is the room really going to be used? Well, let's review our first section here. First of all, remember our definition of an acoustically distinguishable space. It's made up of two things: the acoustical properties that are common to the space and that it's a distinguishable space. There's some kind of definition that we've given to the space or spaces that make it up. We have to remember the purpose. The whole purpose of defining an ADS is where are we going to provide intelligible voice and where are we not going to provide it, or we're going to provide some lesser form of intelligibility. We have to remember those variables. What's the mission or purpose of the system? How much will it cost? And is intelligibility even possible given the room we're speaking about? And then finally, our spaces themselves. What is the common purpose or function of the room? How will it be used? Who's there and for how long? And any other code considerations, like I mentioned, is it a stairwell in a high-rise building? Is it an elevator cab in a high-rise building? Those kinds of things may have requirements that says we have to put a certain piece of equipment in that room, and so we have to deal with how to design it properly. All right. Let's go to how we would define these spaces, and really that starts with understanding the code requirements that are incumbent upon us to meet. Now, Chapter 7 tells us very specifically that a designer must state on the design drawings the design ambient sound pressure level and the audible design sound pressure level. So just to be clear, on a set of drawings, either design drawings or shop drawings, a designer is supposed to have these two figures on there, what they expect the ambient sound pressure level to be and what the alarm sound pressure level needs to be. Now, a couple of rules to follow when we do that. First and foremost, we do have a maximum. We have a ceiling. We cannot go over 110 dB. And this changed several code cycles ago from 120 down to 110 to be more in conjunction with OSHA requirements. And so now those two requirements match. Then we have audibility requirements. Now, it's important to understand audibility is how loud is it? So audibility has some rules. We have to be 15 dB above the average ambient sound level in that room, or 5 dB above the maximum sound level of at least 60 seconds, whichever is greater. So again, think of that mechanical room that has an air handler that's producing an ambient sound pressure level of 70. We need to be above that, or maybe it's producing 90 and we need to be above that. So again, 15 dB above the average ambient or 5 dB above the maximum, whichever is greater. And we measure that using a good high quality sound level meter measured 5 feet above the floor using the A-weighted scale. Often these good sound meters have an A scale, B scale, and a C scale. It's important to use the A scale because that most closely represents what we hear at the human ear. So that's what the code has decided, and that's why that requirement is in there. Next, we have to ask the question, how do you know the ambient sound pressure level of a space before the building is even built or while it's being built? Well, there's not much to go on. The design ambient sound pressure levels can be based on this chart that's found in Annex A of NFPA 72. Now, Annex A is unenforceable code language, but it's really the only direction we have in code, and really a lot of other sources to tell us what we should expect from an ambient sound pressure level. Now, this chart off. Oops, I went the wrong way. This chart often makes me laugh because these are have to be taken with a bit of a grain of salt. We say a business occupancy is 55 dB. Well, okay, that's probably true. However, look at the educational occupancy, 45 dB. I don't know if you're like me. I've got 3 little ones. I go to their school. It's never 45 dB when I go into that school. So you have to kind of weigh these out and understand that there may be other considerations that you have to take into consideration. Additionally, any known ambient sound levels should be disclosed by the space. So if you have a specific machine, like we talked about, an air handler, a piece of equipment like an elevator controller or pump, assembly line, anything like that, you should note that down and then design against that criteria. And also note, if you are using the 2019 edition of NFPA 72, there were some minor changes that were made to this chart for the first time in probably about 20 plus years. For instance, the industrial occupancies increased from 80 to 88 dB on the new chart. So it might be mindful to just check out the latest edition of NFPA 72 so that you're getting the most up-to-date criteria when performing your design. Now, our design methodology. We often want to get started and do our design. And so we go to chapter 24, and it tells us that the loudspeaker layout of the system shall be designed to ensure intelligibility and audibility. And again, those two terms are different. Audibility is how loud is it? Intelligibility is how do I understand it, or can I understand it? Now, if we stopped right here, we could run off, design the system, we'd all be happy, right? But notice that this is talking about the layout of the system. It's not talking about each and every acoustically distinguishable space in and of itself. And the code has an important first step, and it's found in the very next requirement. This item number 2 says intelligibility shall first be determined by ensuring that all areas in the building have the required level of audibility. So we have a responsibility to provide the appropriate sound pressure level, straight loudness in all areas of the building. So people have to be able to hear the alarm. That is why a designer has to define the space. When they're defining the space, you start with the expected ambient sound level and then determine the design or alarm sound pressure level. You have to start there first. Now, once we analyze what audibility requirements we have first, then we start planning out our designations of acoustically distinguishable spaces. And you'll see that's the next requirement in chapter 24. Now, when we follow this process, we discover that there's really 4 types of spaces that we can define. So let's try to break that down. And again, we first determine what spaces will have voice communication capability. And then we ask, are we going to have intelligible voice, or are we not going to require intelligible voice in that space? Now, if we require intelligible voice, then we're going to use intelligible voice loudspeakers in those locations. If we're going to not require intelligible voice, or perhaps a lesser form of intelligibility, we're still going to put speakers in those spaces for the most part. We also may use one or the other of the other options, using an audible tone only, for instance, like a horn or a chime or some other just audible device, or a visual only device. And this is what's often done. Again, the restroom example is probably one of the best that can be made. Now, this is my version, kind of how I break down these 4 spaces so we can come up with a design. The NFPA 72 handbook has a chart in it from Robert Schifoletti, and it's similar, but it breaks it down the same way. And it's really just a decision tree to kind of help you see how to break down the spaces that you want to design. Now, again, we understand that a designer must document what they're doing. So they have to include this ambient sound pressure level and audible or alarm design sound pressure level, and they have to document the acoustically distinguishable spaces. Now, Chapter 18 states that acoustically distinguishable spaces must be determined by the system designer during the planning and design of any emergency communication system. Now, this cannot be kicked down the road to the shop drawing phase, although, as many of you can probably attest to, often it is, or left off entirely. In fact, the documentation of sound pressure levels and acoustically distinguishable spaces is still one of the most missed items on fire alarm shop drawings. Now, what I find is it's usually easier to start with spaces that don't require intelligible voice and will require either visual only devices or perhaps an audible or audible visual device. Now, visual only spaces might include things like high noise areas like mechanical rooms, equipment rooms, assembly line spaces, and the like. It might include noise sensitive areas like lactation rooms, recording studios, and other types of sensitive spaces. It almost always includes toilets and restrooms, but it might also include exterior spaces like docks or porte-cocheres or other things where there's no way you're going to overcome the ambient noise of an idling truck or an idling car, for instance. So again, it's nice if you can define those spaces right off the bat and get those visual only notification spaces kind of out of the way. And then you might look at those that would be provided with audible notification only, things like a mechanical room perhaps, or a tunnel or crawl space that needs to be notified for a particular owner request or reason. Now, I'm not encouraging putting horns and loudspeakers on the same system, but occasionally you might find a situation where the only thing you can do is provide an audible tone which alerts a person to move to a place where they can then receive an intelligible message. Next, we want to focus on all of the other of the areas of the building that will be provided with voice communication, with the idea of having most areas require intelligibility. And that's the goal after all. We want to be able to communicate to people and we want them to understand the message that's being played. Next, we define those areas that will not require intelligibility or less intelligibility is probably the better way to say that, even though we'll be providing loudspeakers in those spaces. Now, the annex of the code clearly states a number of locations that might not require intelligibility, and they include some of the spaces we've noted, like elevator cars and individual offices and closets and storage rooms and the like. Again, we have to go back and remember what those spaces are being used for, even if they're being called by a certain name, what is really going on in the room. Now, the key is to know if you're not going to require intelligibility in a given space. If not, why not? You need to be able to explain why you wouldn't be doing that. Is it because of the physical properties of the space? Is it because we have too much reverberation because of the physical characteristics of the space? Is it too small or too big? Or are we going to use alternate or supplemental notification to help overcome some of our acoustic difficulties? So let's review quickly. Again, sound pressure, that's where we start. We have to be able to identify the ambient sound pressure level and audible or alarm design sound pressure level for all the spaces of our building. When we design, we first provide audibility in all spaces. That's our first responsibility. Secondly, we go in and identify the intelligibility requirements. And really, we look at 4 types of spaces as groups: those provided with intelligible voice, those provided with less intelligible voice, those with audible only, which again might be few and far between, or those with just visual only, just providing strobes as an example. All right, well, let's see how a designer can really put into practice what we just learned and what that would mean for the authority having jurisdiction who's going to review this design. Now, a quality ADS design requires a designer to take responsibility for all of the factors we've talked about so far. Now, a designer can either pass the buck or figure out a way to put the pieces together to take responsibility for his or her design. So again, let's look at a few practical ways to show designer responsibility and how this might affect what happens with the AHJ. We talked earlier about the need to understand the expected ambient sound pressure level within various spaces in order to properly design and designate ADSs. Chapter 18 makes it very clear that this shall be documented by the designer. So, how could this be done? Well, a very simple note on the drawings might be sufficient. This note, for example: this building is a B occupancy and an ambient sound pressure level of 55 dB, which we got from that chart in the annex, is expected. The audible design sound pressure level shall be a minimum of 70 dB throughout the facility. And of course, we place this in the most boring AutoCAD font we can find. Now, keep in mind what this is actually requiring. This kind of a note requires really very little effort, but it may limit the designer's intent of providing intelligibility in some places, because this is now requiring that every space have 70 dB as a minimum audible value, which may be too much or too little for some spaces. This might be a better approach. A chart like this may provide more flexibility in the design of individual acoustically distinguishable spaces, and it also allows a better testing approach to the various spaces. Think of the theater space we were looking at in our earlier example. In an unoccupied time, it's a very quiet space, and we don't have any ambient sound level to speak of to overcome. But during an active performance, you might have 90 dB, you might have quite a bit more than that. Think of gunshots, explosions, other things that they might feature in a theater performance. So we're getting pretty high. Once we're cresting 100, that's a pretty high number, and we need to start thinking what else we can do. Now, the second piece of that, once we've laid out our sound pressure levels and showed those on our drawing, now we have the responsibility to do the exact same thing to our acoustically distinguishable spaces. And we can build on what we just created for the sound pressure levels. So how, again, can we account for this? Well, one option is to provide a written note, possibly with the sequence of operations on the drawing, that notes the various ADS definitions and uses lists of spaces. We're going to provide intelligibility in hold rooms and in public spaces and corridors, etc. Just kind of this lists of spaces. Now, based on the size of the building you're dealing with, this may indeed be the only way to do this in a time and cost-effective way for your ADS design. The building may simply be too big to provide a greater level of detail. But smaller facilities may present other options. This is an example from the NFPA 72 handbook. Again, a diagram provided by Robert Schifoletti. In this case, he took a nightclub and color-coded the drawing, much like you would a key plan, and he's using these various colors to indicate where intelligible voice will be required and where intelligible voice would not be required. Now, why did he use all the colors he did? Why did he break them down the way he did? That's up to each individual designer, but it gives an example of how this could be done. This is another option and may be preferable. Using a chart with information that includes the location or definition of the space, the minimum requirements that the designer is providing for their ADSs, the devices that they're going to provide in those spaces, and other important notes could be very, very helpful. This could be color-coded to the floor plan, but that's a lot of extra work and maybe overkill. But the chart itself may be a good way to go. And so we can identify, well, we've got this pre-function space. We're not going to provide intelligible voice because it's not possible due to the reverberation and the construction of the space. But we are going to supplement the space with visual textual notification, as an example. So this becomes a really good way to define or show your ADS definitions. Now, this is another option. This is what one designer did. They used a Revit, the BIM model, to show hatching to designate their ADSs. And so they basically got kind of 4 definitions of space where they're either going to provide intelligibility or not. However, one issue with this is that they happen to use the reflected ceiling plan of the Revit model to show their ADSs. So the hatching used for the reflected ceiling can get confused with the hatching used for the ADSs. So you really kind of struggled to figure out what are they providing here. So be careful in how you choose to represent the information on the drawing. But at least this designer took some responsibility and tried to define the acoustically distinguishable spaces. So at least they made a good faith effort. Now, the AHJ provides an interesting wrinkle in this process. The AHJ is charged with a lot of responsibility, and one of them is to review our plans and approve our plans. Well, that can be quite a challenge for some because some may just struggle to understand fire alarm systems in general and may know nothing about sound or intelligibility. They may not really understand why you are making certain decisions. It begs the question, what if they disagree with your classifications of an ADS? Well, hopefully it doesn't come to the boxing gloves shown, but the answer is it depends. Are they concerned about the way you define the space? Or is it just the fact that they want you to try harder to obtain intelligibility in more locations in the building? Again, it requires a dialogue to understand what their difficulty with the design might be. Additionally, the omission of information or a true design does not make your job any easier. In fact, it makes it much harder. If you don't design or adequately define an acoustically distinguishable space, think about what happens during commissioning or acceptance testing. NFPA 72 clearly states that quantitative measurements are not required, but they are permitted. So in lieu of a good design, an AHJ could require quantitative measurements of a sound pressure level using an intelligibility meter and measuring it on an STI scale or a CIS scale. However, if you provide a good design, you'll be recognized as an authority. The AHJ will simply follow or maybe make a few minor suggestions. But again, if you don't provide a true design, you could end up in a situation like this where everyone has an opinion about the intelligibility of a given space. Now, I will say this picture is a sound training class, so don't panic. The AHJ was not putting us through a lot of problems here. This picture is courtesy of Sid Oddcon. That may or may not be a group that you're familiar with. If you think you need more training on audio systems and understanding audio, this is a great organization to get trained by. You can just go to Sid Oddcon, Google that in. That'll take you to their website. It provides very good training, very cost effective as well. So just a shameless plug for them, but they're a very good group to get to know. All right, so let's just review for a minute. We have to document our ambient and design sound pressure levels. We can do that with a simple note or even better, a chart of spaces. We have to document our ADSs. Now, again, we could do that with notes of types of spaces. We could do a chart of spaces, or even color-coded or hatched out floor plans. But keep in mind, whatever you do, it has implications with the AHJ. They have to be able to review and approve our plans. If there are definition disagreements, it's going to have an impact on commissioning, so we have to have that communication with them. All right, let's finish up our presentation by looking at what can be done to improve individual acoustically distinguishable space designs. We're going to look at 6 ideas to improve our designs. The first is something I called a localized ADS, and this goes back to the imaginary boundaries of an acoustically distinguishable space. For all intents and purposes, this is a very small ADS. It's usually a small subset of a space. It's taking a very focused approach to meet a very specific need. Well, let's think of some examples. Assembly lines. An assembly line, we have workers that may be working right in a given area, and they're always in that given area. So can we provide some kind of intelligible voice for them rather than trying to flood the whole area with sound? Control rooms, customer service counters like at an airport or an airline gate, providing intelligible voice right where people are gathered versus trying to fill the whole space again. Stage control facilities or atrium reception areas. This is a small little ADS developed just for the pre-function area of our acoustically distinguishable space in our theater, for example. We're providing a very focused approach on the folks because we know where they're going to be. Now, localized ADSs come with a few issues or concerns to think about. How will we be mounting or locating a speaker? Maybe it's in a desk or a console. Maybe it's hanging down right above a location. So how are we going to physically mount it? How loud or what's the wattage that we're going to select for the speaker? If it's in very close proximity, we might not need to be that loud. In fact, we probably shouldn't be that loud. If there's an ECS microphone, like at an airport gate or even in a fire command center, do you need a speaker cutout to prevent feedback when making emergency announcements? And do you need to marry the loudspeaker with some kind of visual component like a strobe? And if so, how are you going to do that? Our second suggestion is to use an existing public address system or sound system to broadcast emergency messages. Now, this has huge advantages as the quality of most commercial grade paging and public address systems is very good. Most systems are inherently designed for intelligibility from the get-go. And being able to use these systems can save significant money in providing a dedicated audio fire alarm system, for example, especially in very large facilities. Now, a couple of examples of where this comes into play. Airports. Airport paging address, public address systems are very reliable. This is a picture from an amplifier rack in a major airport. Each of these amplifiers can be 100, 200, 300, even 500 watts of power. And they're in these amplifier racks with backup amplifiers and the like. Excuse me, highly reliable and good quality with a lot of options. Some building public address systems that are quite good. Now, again, we're talking high-end, commercial grade or better, not a system you'd run and kludge together from a store. And even professional sound systems like we'd see in arenas or theaters or other large venues, convention centers and the like. We can use these because they are made for intelligibility and can provide some examples or some advantages. The problem, though, is with big advantages comes significant issues. And here's just a few of those. First of all, the complexity of the interface. We have to figure out how to marry a fire alarm system with a commercial sound system. And that can be pretty challenging. It's not as easy as just providing a single input. We have to think about the messaging requirements that might be required. These systems are often very good at providing intelligible voice messages, but not so good at providing pretones like a slow whoop or temporal 3. Message priorities. How are we going to dictate what has priority over something else. So would a routine paging announcement override a fire alarm announcement, as an example? Secondary power. This is probably one of the biggest ones. Being able to provide battery backup that's equal to the fire alarm system for all of those amplifier racks that we just looked at in that other picture can be very, very challenging and present some significant cost as well. What about systems that are not on all the time? Can we provide a module that turns a system on so that we can use it? Well, yeah, we can. There are modules to do that. However, that requires some pretty good design, and you really got to know what you're doing in order to do that. What about systems that can be disabled without supervision? If someone were just to turn off the amplifier or disconnect a piece of equipment, will we know about it? Will the fire alarm system receive a signal if that were to happen? Now, additionally, when we want to use house sound systems, NFPA 72 has some additional requirements. In fact, it requires the system to be evaluated or to have a risk analysis to really analyze if it can be used. Now, the house system needs to meet performance requirements of Chapter 24 and the Emergency Response Plan, but not necessarily the prescriptive requirements, every single thing. So that's really why we need a risk analysis to tell us what we need to do. And again, that risk analysis needs to address some of the potential concerns we just talked about. Visual notification, message priority, speaker volume controls, circuit integrity and supervision, textual visual notification, and the like. This can be an important step, but again, might be worth it in very large facilities. Now, where it's not practical to capture an audio system, we should provide audio shunt. Audio shunt just does away with the audio and visual distraction of a signal and also lowers our average ambient sound pressure level. So whether that's a local system, a cable television system like you'd have at a bar or restaurant, advertising and video boards that might distract from your visual notification in a building, providing audio shunts is quite simple and quite cost effective. In most cases, we're killing the power or the feed to the device. Some good examples of that might be bars, like we mentioned, lowering that average ambient sound level so that we can overcome that and hear the message. Nightclubs. I ignored social distancing rules last night. Took this picture. I'm just kidding. Pre-COVID, nightclubs like this existed, and there's obviously no possible way you're going to see or hear a fire alarm signal in a location like this. We have to be able to do a lot of shunts in this scenario in order for everyone to understand what's going on. And the same is true for stages, for theaters, tenants in malls or in airports. All may have different scenarios, but providing shunts is important. Now, some things to consider. What really is a distraction and needs to be shunted? Is it just a small radio, a little Bluetooth radio that's playing, or is it something much more significant that really affects hearing of audio or alarm signals? Audio shunt is relatively easy and low cost. It's often just killing the power through a relay, but we have to consider what happens when we reapply power. Now, will the system just come back on? And if not, that's going to make the tenant or the owner very unhappy. So we need to test these things, try them out, and make sure that what we've put in place isn't defeated right after the technician walks out of the door. The fourth suggestion is to use the use of non-listed speakers. So starting with the 2016 edition, the use of non-listed speakers is allowed. Now, this is an open acknowledgement of the limitation of fire alarm speakers traditionally that we've used, although they are becoming better, the ones on the market. The goal of this allowance is to enhance intelligibility. And really, in the 2019 edition, we changed the language a little bit to say where listed loudspeakers do not achieve the intelligibility requirements, then you can use non-listed loudspeakers. Now, a few examples: high quality commercial speakers that come in all shapes and sizes, serving different purposes with different mounting. Even line arrays. Line arrays are used in large spaces like atriums and malls and other places. Very, very highly intelligible because it aims or directs the sound where it needs to be without being reflective. But often these commercial options are quite pricey and present some challenges on their own. The huge advantages of using quality speakers present some challenges that we need to be aware of. The biggest and first is supervision of wiring and speakers. Our fire alarm speakers are very used to providing a supervisory voltage through the device and then removing that when the alarm occurs. However, commercial speakers aren't like that. They don't understand that. So we might have to provide a somewhat complicated interface, perhaps a dedicated circuit tied to a dedicated amplifier with an audio input from the fire alarm system. We'll need to provide secondary power for this equipment. We'll also probably need to provide some labeling so someone just doesn't come over and turn off the amplifier and thus negating all the work that we've done in the design. Now, one nice thing about what's occurred since 2016 is we now have a lot of listed speakers. So this is one of the best high quality, high fidelity speakers that comes from JCI. Very, very good speaker and listed, obviously very compatible with your fire alarm systems. This is a fire alarm speaker. That's a 2x2 ceiling tile speaker. It's made by Qualm out of Chicago. Very, very high quality. In fact, you can even get these with a junction box in the middle to place a strobe right in the middle or any other device. Very, very high quality, listed for fire alarm and compatible with fire alarm systems that are on the market today. Hyperspike products. If you're not familiar with Hyperspike, they provide a very nice line of unique. This one, the round one, is a omnidirectional, very good in your industrial facilities, the larger facilities, and provide very good quality. And there are even now fire alarm listed line arrays. These are tremendous. They provide tremendous benefit for acoustically challenged spaces. We can also use modeling software. Modeling software presents a tremendous opportunity to understand a space even before it's built. Now, there's a variety of packages that are out on the market. The most commonly used is EaseEvac, and it requires some expertise to figure them out, but it can help. Let's go back and take a look at the space we noted earlier, that pre-function space. Modeling software can be used for acoustically difficult and even complicated spaces, but the spaces themselves still need to be rather simple because the software has some limitations about how it operates. We need to understand that there's only so much we can do to recreate this space within an acoustic modeling program. Once we use EaseEvac, the software will tell us a lot of the information we need to know, including sound pressure level, signal to noise ratio, and even speech intelligibility calculations using 3 different scores: an STI score, a CIS, which are kind of the most commonly used, but also an Alcon score. And so instead of just relying on subjective ratings of intelligibility, we can actually do quantitative measurements. At that point, then we need to draw the space. We need to enter the physical properties of the room, everything we talked about in the beginning of our conversation: the floor, the walls, the ceiling, the materials, etc. We enter the type and location of the loudspeakers that we're using, and then we measure it. So again, we've got our space here. This is what the designer provided. This wasn't my design, just one that we did some modeling on. They provided 5 regular fire alarm speakers in this space. So when we plug that into the modeling software, this is what the sound pressure level of those specific fire alarm loudspeakers that we provided. And we find that in this space, it averages about 70.2 dB across the space. Well, what was our design sound pressure level? Well, didn't we say that the ambient sound pressure level in this space was going to be about 65? So really, we need to be around 80. So this design is not going to even provide our audibility that we need. So we have to clearly do something. And that's the nice thing about these modeling softwares. It allows us to see it in advance. Now, this is that same space, same layout, and it gives us a CIS score of 0.53, which again is in the poor range. So we need to do something else. In this case, we looked at several other scenarios, and I'm not going to go through them all, but this is one that provides a 9-speaker design rather than 5. We lowered the tap settings, and lo and behold, by adding more devices at a lower tap setting, we get an average sound pressure level of about 83 dB throughout the space. Definitely louder, and probably and certainly more effectual at achieving our results. And this is that CIS score, which gets as high as 0.6. So we've improved it. Still not great. We'd still probably want to do some other things to this space, or think about other things we can do. But we certainly have a much more uniform pattern, especially in the green areas, that we have something to work with here. Now, a couple of things to note with modeling software. There has to be a cost, effort, and benefit ratio. It's not practical for all spaces. It may simply confirm what you already know, like we did in advance on our pre-function space, but it can be used as a communication tool with the architect, the AHJ, and others. Obviously, there's some costs with the program and training. You have to have the modeling files for each specific type of speaker, and certain types of speakers like directional or aimed speakers may not work in some programs. Now, our last suggestion is using enhanced visual coverage. This is an acknowledgement that sometimes a given space can only be so good when it comes to intelligibility. So we can enhance or supplement a space with visual notification. This may also address a need for other languages. If we have a requirement in our situation to provide other languages, this might be an option to do that. Now, there's various ways we can do that. Obviously, we can use our strobes. We can do video screen capture like you do in an airport by capturing the flight displays. We can capture advertising displays and display a message on those. We can use LED text signs, which for your situation connect directly to the auto call panels and are quite effective, or even static signs occasionally. Now, again, a few issues to be aware of. There is the interface design. Interfacing with video capture and advertising signs can be a little difficult. We have to think about supervision. Are we going to require supervision? What's the long-term maintenance when the IT guy comes in and changes the programming on that monitor? Does the fire alarm capture still work? And what's really a distraction? You know, in the case of these menu boards, do we really have to capture those? Well, probably not. But we need to think about what's really going to help us. So our 6 items that we talked about, it is possible to improve individual designs. Go small, go specific, provide a localized acoustically distinguishable space, even if that's with an imaginary boundary. Capture audio, use what you have, but again, be aware of some of the limitations. If kill what you can't use, right? Shunt the audio, shunt the distractions so that you can provide a better design for your fire alarm. Use non-listed speakers, or even better, use new listed speakers that you may not be familiar with. Modeling software can really help in unique spaces or places where you might have unique challenges. And use enhanced visual coverage. Supplement with visual items that you can use that might be very helpful both for the public and for intelligibility. At that, I thank you for your attention. Anne-Marie, if there's any questions in queue, we'll answer those. Sorry I ran a little late, but not too bad.
Not a problem, and it's great information, so that's wonderful. There are no questions in queue, but we can open this up. If anyone has any questions, just unmute yourselves and let us know if there's something that Larry can answer. We'll give people a couple seconds here.
While they're thinking about that, Anne-Marie, I'll give the plug. We are going to do a kind of a second version of this in a few weeks through the AutoCall Academy we're going to do a presentation on improving intelligibility through the use of technology. And we're going to look at some of those new things that we kind of alluded to, and also look at some design tips. How do we actually design and lay out loudspeaker systems for emergency communication? So anyway, shameless plug. I think it's in a few weeks, but keep on the lookout for that.
Yeah, that'll be taking place on July 9th. So we will be getting invitations out to everyone, and I'm sure everyone will enjoy that presentation. So, you know, oh, do I see something coming in? Hold on. Did someone have a question? Oh, I see it now. Hold on. Will this webinar be posted on eLearn? I don't know that it'll be posted on eLearn. I will talk to the training team about that. We will get this out to you though, regardless of it being posted, or if we need to send a link or something. So we will make it available. Okay, so if there are no other questions, we'll let everybody go for the day. And Larry, I'd like to thank you again for taking the time to share your insights and provide us with all this valuable information. And I hope you all have a great day.
You're most welcome. Be safe. Take care.
Thank you.